那你这个最终还是讨论不同时间的这个解决方法，是不同时间的解决方法。
因为在从0到100这个时间段里面，你应该放掉；从100到200的时间段里面，应该放掉。
Okay, let's begin. Today we will cover stochastic recitation and quadratic programming. I try to speak as slowly, so if I speak too fast, please let me know, because my English is not so good. And here is a typical machine learning problem. It usually has the form penalty or regularizer plus a loss. So our goal is to minimize FW. F is the objective. FW equals to GW. GW is the penalty, usually controlled the model complexity. For example, we can make sure each element of W is not too big. And the second term is 1 over n FW yi xi. F is, we usually call it a loss term. It is the loss if we get the wrong prediction. So we have a two term here. Sorry. And there W is a vector. It's a p-dimensional vector. We have n samples, si, yi. Xi is also a p-dimensional vector. Yi is usually a scalar. So now, we usually consider both G and F are convex. We call it convex programming. And today we only consider differential of F. That is, the gradient of F is always exists. And also we let G equal to 0 to make it simple, to make for simplicity. Take an example. We can choose F to be minus log P given the probability of yi given sample xi and w. W is the model. Si is the sample. So given the model and the sample, we want to estimate the probability of yi equals to 1 or yi equals to minus 1. So it plug f into the objective function, we get maximal, the log likelihood. It is usually the problem we have in machine learning. We want to maximize the log likelihood to estimate W. So far so good. And so we consider how to solving this problem. We have a problem. We want to minimize it, but we want to get the optimal solution, W. Okay, here is the gradient descent. So we first look at the right figure. So it has ellipses. Ellipses is the contour of the object function fw. Here is a two-dimensional example. So w is a two-dimensional vector. It's x and y. And so the value on all ellipses are equal. The large ellipse has a large optic value. The small ellipse has a small value. So the minimizer is on the center. We want to find the center which minimizes the objective function. Now how to find it? Usually we do not know the shape, the actual shape of the ellipses. So actually we know is that there's a way that just working along the here or something like that. You start a position x0. On that position, we work from that position toward the center and take a step to x1. And on x1, we take a first step to x2. If we ensure we always work toward the center or the minimum, maybe after some steps we get the position. So because we usually do not know the actual shape of the ellipses, so what we know is that at a particular point, usually we can calculate the gradient. The gradient is also orthogonal to the contour of the object function. It is point from the small value to the higher value. So if we work along the negative direction of the gradient, potentially we can get a small object value. So we have choosing the direction. Another question is how to choose in the step size. Yeah, we talk it later. So we have a gradient descent. We first on the left hand. So we first choosing the initial W0 and repeat. So we start working. For each step, we get the new position by the old position WT minus eta t. Eta t is just the step size, it's a scalar. And the gradient of f is the object function. Wt is so delta gradient of f Wt is the gradient of the object function at the old position Wt. And we use the selective, the opposite of the gradient. So we hope to decrease the object function. Okay? And we keep working, we keep iterating until we stop. So how to calculate the gradient of the object function? Remember that f is summation of small f, w, o, x, y, yi, and si. yi and si are samples. We are on the average of the loss on n samples. So take gradient of f equals to take gradient of each f on each sample and do the average. So this is how to calculate the gradient. Now how to stop it? For example, if after some steps we find the new position we get is quite near the old position we have, probably we get a stable point. We get a smaller, we could not get out because each time we reduce the object value. Also, we can check the value of the gradient. If gradient is equal to 0, surely you cannot go any further. So these two things you can get stopped. If maybe some values, for example, very small values. And now we have a direction. The next question is how to choose in the step size. It really matters. For example, if you have a very large step size, for example, eta t equals to t, we start from the top point. This is the initialized point. We work. The first step is good. Second step, okay, bad. And anyway, I don't know what it does. So, but if we using a too small step size, we still start from the top point, and after 100 iterations, work 100 steps, we still on the halfway to the minimizer. So it's waste of electricity. We have a very simple way to adaptively choosing the step size. We call it backtracking line search. It works like so. So this works as first we choose a parameters beta is between 0 and 1, and we start within a linear rate eta equals to 1, and the start iteration. So here is the while loop is the new step here. Look at the right side. It is xt is the old position we have, actually the current position we have, the current model we have, and eta is the linear rate. The next is the gradient of the objective function at that point. So it is a direction here. And so the right side is that if we start from WT and within step size eta, we get a new position and we calculate its objective value. This is the right hand. The left hand is the first. This is the right hand. This is the left. So the right hand, the first term of the right hand is the objective value of the current position. It is what we have. And the second is a positive constant. It's about eta is about the gradient, so it's a positive. So we hope, so if the new position we have is not less than the current position we have, and minus some constant, some positive constants, we decrease the learning rate. That is eta equals to beta times eta. This for loops can be, it's not infinite for loop, for example, because each time we decrease eta, we also decrease the value of the second term on the right, the right hand. So on the extreme case, eta equals to 0. So we do not. So on this step we do not work, but we can jump out for the for loop. But on most cases, after some iteration, we can find a new position, a good eta, and we update, and then repeat it again. Okay, so far so good.
So you're saying if you're not getting closer to your maximum, then you decrease eta?
Yeah, you always decrease the eta. Okay, I can show you why on the left example. Here's an example. So still the data, still the same start point. We start from the top cycle and start working. On the first step, we work step size with 1. It's good because it makes sense because we are far away from the minimizer. Take a long step size is safe. We want to take large step size. We want to get near to the minimizer as soon as possible. So we take a large step size, and then we take the same step size second. But after about 4 steps, we decrease the step size because we are near the minimizer now. We want to make small steps so that we do not pass or just ignore the minimizer. So at the beginning, we with a very large step size, but at the end, we want to make step size very small, so we can get exact point of the minimizer. So that is why usually you keep decreasing the learning rate is good. So it's 13 steps. Okay.
So in each iteration here, that you need to come to the best step size, right? So that you know how large you.
It's not actually. It's not step. It's not the best. Actually, it's just very easy. Just decreasing the eta. So if you want to calculate the best, you want to do a further minimization within the follow. For example, we just on the left side, we just minimize the left side term with respect to eta to find the minimum, the best eta. Usually it is expensive, and you can do that to save. For example, if you're using the best eta, maybe you can get on 10 iterations, but each step you get much more expensive. It depends. So on the data and on the algorithm you have, you can do that actually.
Is there an assumption that there's only one global optimum?
Yeah, it's Convex programming. Sorry, maybe I didn't mention that. It's Convex because the counting here is ellipsis, so it has a unique global minimizer, and we are covering the quadratic programming. So here comes stochastic gradient descent. Remember the loss term we just have is the average of the loss term on each sample we have. We call it empirical loss because we just we get some data, but we don't know what F exactly looks like. So we're using our data to guess what the shape of f. So we call it empirical. Actually, a better way is just if we know the distribution of the data, or we can get a better estimate of f. We just take an expectation on f based on yi, and xi. Is the video okay? Sorry. And you get a better estimate of f. It's now about fw. So suppose we have infinite samples drawn from the underlying distribution. How do we do? One way is that we still begin within a model, within an initialized model. And each time we get a sample, we just calculate the gradient immediately. Don't wait something others. And update the model. So still you have eta t is the step size and the gradient. But the gradient is now only respect to one sample here. Because each time we get one sample here, but we have infinite sample. So we can get many runs and get the result. So, because usually xt or yt is randomly drawn from something. We call it a stochastic gradient descent. And this is because the objective function to minimize is just the expectation on f. So it has a very nice theoretic guarantees. We will not cover here. We check how to run this algorithm. On practice, usually you have only 100 samples or 1,000 samples. You do not know the underlying distribution. Because if you know, you can do sophisticated algorithm. You don't need to using gradient descent or something like that. So on practice, you usually only have a small set of samples. So how to do? Usually, a common choice is that we simulate the infinity string by each time we randomly pick up one sample from the data you have. For example, if you have 100 data, and I want to repeat 1,000 or 10,000 times, each time we randomly pick up one data from your 100 data samples, and calculate the gradient, take a step size, and update your model. So if I do 1,000 times, I update the model 1,000 times. So comparing to the gradient descent, the gradient descent is that for each step, we calculate all the gradients. We calculate the gradient on all the samples and do average. And using that average to update the model. Now, we have each time we just calculate the gradient for one samples and do the update. So it's a trick is that, let me talk more. So if you have 100 samples, so you take gradient, you first on each step, you take the gradient and do the average. You modify the model. It's the gradient descent. For the stochastic gradient descent, you first take one gradient, one sample, and compute the gradient and update the model. So for the second sample you draw, your model is changed. The gradient is different now. So it's a difference. So
for the infinite stream of samples, so do we still need to, like after I update the W's, do I still need to look at the samples I already used, or just drop the samples I already used?
Usually case just put it back.
Put it back. So what do we have like a circle? Like do it?
Usually do is that you have 100 samples, you randomly permutate it and iterate, and randomly permutate, iterate.
Okay.
It is usually we do that on that way.
All right.
So the difference is that you take for both stochastic gradient and gradient descent to scan the whole data set once, gradient descent make one update of W. But for the stochastic gradient, you make 100 update of W.
So does stochastic gradient descent guarantee the same global optimum as the regular gradient descent?
Yes, yes, exactly. So certainly there's assumptions about data. So under the same assumptions, the gradient descent and the gradient descent all converge to the same optimal global minimizer. And the stochastic gradient has a better convergence rate, something. It's not better, it's 1 over square t. So here is the result. Still you have a two-dimensional example here. The ellipsis here is the contour of the object function. You start from point from the top left point here and start work. You can see that there are some steps are good, the long steps and the work toward the minimize. But most steps just work random. So, and the right side is the steps versus the object value. You can see that there are 1, 2, 3, 4, 5 steps decrease the objective value significantly. But on the most case, it's just the progress is little. So why? Because data is quite noisy. Each time for stochastic gradient descent, each time you're using one data to predict the gradient, the directions. Maybe if the data is quite near, it's noisy. The direction you have maybe is not point to the minimizer, it's point something else. So for that case, you get correct direction, you get big progress. If you get wrong directions, you just maybe you even increase the objective value. So the first observation is here. The object value does not always decrease for each step. But on general case, it decreases. And now comparing to gradient descent. Gradient descent it has a figure here, 17 steps. Each step makes good progress. For stochastic gradient descent, many steps. Some steps make good progress. Some steps are not. But for gradient descent, for computing the gradient, it scans all the samples you have. But gradient descent, each step you compute the gradient based on one sample. So the computational cost of stochastic gradient SGD is less than gradient descent. Take an example. If you have 1,000 data, so for SGD, the cost of each step is like 1,000 times smaller than gradient descent because you only take one sample and gradient descent take 1,000 samples. And assume gradient descent make 10 iterations to get stopped, to get the minimizer to converge. But stochastic gradient need 1,000 iterations to get the point. But still, SGD wins because now you have 10 times faster than gradient descent because the computational cost is the cost of each iteration times the number of iterations you have. So in many cases, gradient descent still can win gradient descent. And we said before that the reason you do not get good progress is because the noisy of the data, the wrong directions. So here is a trick. We call it mini batch. So instead of picking one big samples, we pick 100 samples and do an average. You have a noise, okay, you have a noise data, but we pick more data and do average. Suppose the data is much better than one samples. So in that case, you make each step more expensive, but you can get good directions. It is still worse. Because 100 samples is still small comparing to the actual sample you have. So mini batch maybe accelerate conversion rate, especially when the data you have is very noisy. Okay. Here we talk about relationship between perceptron and the grid SPD. Remember, perceptron is just first initialize the model you have. W is a vector here, and we repeat. Each time we get a sample, yi and xi, and we do a prediction by doing the product of w and xi. So if the prediction is correct, that is not correct, that means yi times wxi is less than 0. We update our model. The update is yi times xi. So if you do a good prediction, you just keep the model the same. This is perceptron, and you just iterate. Now, for the SPD, you fix the linear rate eta equals to 1. And that is a loss function f w x equals to max of 0 and minus yi times w times xi. On that case, you do a gradient, you calculate the gradient of f. So if you do a good, correct prediction, if you do not do correct prediction, that is yi times omega times w times ai xi is less than 0. You get the gradient minus yi times xi. Otherwise, you get 0. So put this back, you get the perceptron. So far, so good. Okay, we are done.
So one more question.
Mm-hmm.
So is the stopping criteria the same as gradient descent?
Sorry?
Is the stopping criteria for stochastic gradient descent the same as the regular gradient descent?
Step size.
Stopping criteria.
Sorry.
When,
Stop? Yeah.
when do you stop?
Yeah, you can use the same.
But the objective function is a little bit jumpy, right? It's not that.
Yes. Usually, you calculate, do average for at the past 10 steps. There's no progress. You stop, or you can do that. Or if you're using a mini batch, it's very stable. You can use in the same stop criteria as gradient descent. Now we talk about where's the okay. Now we talk quadratic program. So what is quadratic program? Is you have a term here. First, we want to minimize the objective function, which is 1 over 2 transpose w times q times w. So the first thing is a quadratic term. It's because w is the variable now. It's the generalization of quadratic term to the vector space, because q is the symmetric square matrix. Okay, let's see you remember what is symmetric. That's qij equals to qji. And the sector is a linear term, c transpose c times w, which is the objective term. And here is constraint, different to that machine learning, different to the stochastic gradient gradient, is that here we have a constraint now. So there's two types of constraint. The first is inequality. It's A times W is less or equal than B. A is a vector. A is a matrix. W is a vector. So the less than operation means the left side is a vector, the right side is a vector. Less than means each element of the left vector is less equal than each element of the coordinate element of the right vector. So if A is a M times N vector matrix, you have M constraint now. For the equality constraint, E times W equals to D is the same. If you have P rows on E, you have P equality constraint. So we call it constraint optimization. It has a form to minimize the objective term, and you have some constraints. We call W is feasible. So if it satisfies all the constraints you have. So the solution to this optimization problem is first it should be a feasible point. Then it minimizes.
I think there's a typo. The dimensionality of D is P, not N.
Sorry. D and P is different. It's M and P. Sorry, but it's a vector. And we call W a local minimizer if for any feasible U around W. The round is generally adhere. Maybe it's very, very near. And we have FW is less equal than FU. F is the objective term here. We just make a symbol. And for global minimizer, for any feasible U, we have FW is less equal FU. First, a global minimizer is certainly a local minimizer, but it's not true on the opposite position. A local minimizer is not always a global. We will show example later. Now here is an example. It's a two-dimensional problem. And the ellipsis here is the contour of the objective function. And if it's convex, quadratic term is always ellipsis. On the high dimensional is ellipsis ball. On the three dimension is a ball. On the high dimension is also a ball. So, and the center is the minimizer. And the cyan area omega here is the feasible area of the inequality constraint. So remember that each row of A define the half space. You define row because for each x times omega W equal to some scalar is a line on the space. And for inequality, it is a half space. So here you have 5 edges of the omega have 5 edges. So you at least have 5 rows on A. So each row of A is half space, and maybe some is on the edge, some is on other places. And the red line is the equality constraint. Is only one constraint here, because on the two-dimensional, equality constraint is equal to lines. So think about if we only have inequality constraint, where is the optimal position? It is here. It is here. And if we only have equality constraint, so the minimizer is here, because you should be on the line. So far, so good. So here, if Q is positive semi-definite, that means for any x vector x transpose times Q has x is large equal than 0. It's a generalization of the positive scalar to the vector spaces. Then the objective, if Q is semi-definite, then the objective function is convex. That means if any feasible W exists, any local minimizer is also global minimizer, because it is convex. And there is at least one global minimizer. It makes sense. If Q is definite, that means x transpose x times Q times x is larger than 0. Then we call it strongly convex. Also true is that local minimizer is also global. The difference is that you have a unique global minimizer. So here is two examples here, like the following picture. On the right hand is a positive definite. You have two-dimensional example. You have contours, and this is the minimizer. You have a feasible area omega. Here, dot is the minimizer. It's the global minimizer to that problem. But the thing is different if you have indefinitely Q. Here you have 4 area here. The plus means that value is higher. The object value is higher. The minus means less. So you have dot. You have the dot on the right and the dot on the left. Both of them are local minimizers because all the point around this point is less than this point, is larger than this point. But only one of them is global. Another guy is just a local minimizer. So for the non-convex optimization, maybe you find a minimizer, but you cannot sure it is global or local. If the Q is equal to 0, it is quadratic programming reduced to linear program. Linear programming is maybe the most famous problem or optimization. It's widely used. So in general, QP is until-card. It can be reduced to max-card problem. But there are several algorithms to solve convex QP. For example, Cauchy-Lewis method, interior point method, something like that. We show example here. Here is two-dimensional example. You have two variable x and y. Both are scalar. So your quadratic plane is a ellipsis. It's centered at x equals to 0, y equals to 4. So this is the center, and this is ellipsis is here is the quadratic term. You have 1, 2, 3, 4, 5. You have 5 inequality constraints. First there is x plus y less than 7. It's this line. All the x, y should be under this line. And the second is minus x plus 2y less than 4, this line. All the points should be below this line. And also x is larger than 0, y is non-negative, y is less equal to 4, this line. So you have a feasible area here. And certainly you can calculate, you can find the optimal solution here. Is x equals to y equals to 3. Now, you can see we convert it to a standard quadratic program. So first you have the q is equal to, so there's no 10x times y. So q is diagonal. And because here is the 1 over 2 term here before q. So q is equal, diagonal of q is 2 and 8. And here is, first here is the linear term, minus 32y, x is 0, here is c. And here is 5 inequality constraint here. The first row is x, first column is x, second column is y. So you can write down the A here. B is also can be simply write down. There's no equality constraint. So E and D are equal to 0. So now how to solve it? You can use it if you know quadratic program. If you know Cauchy-Lewis method or interior method is good. You can write some program. If you do not, it's okay because there's very standard toolbox for you to write. For example, using MATLAB, it's just x equal to quadratic programming Q, C, A, and B. So you get the solution here, x equal to 2 and 3. So if you use MATLAB. Also, there's another C++ toolbox or Python toolbox you can use it. now we talk about SVN 2P. We call that support vector machine. The object function of support vector machine has we minimize 1/2 the square of the law of W. It is the summation of quadratic summation of square of the element of W. And the constraint is inequalities. Is yi times xi times W plus b0. b0 is the bias. Certainly, W is a vector. YR and xi are samples here, which we want to make sure it is not less than 1 for any samples here. So it is quite simple to write down as a quadratic program. First, you have Q is the identity matrix because you have only the log here, and you have n. If you have n samples, you have n inequality constraint. So A is at least have n rows. Each row is minus yi times xi, and the coordinate B is just yi times b0. There's no equality constraint. So en d equal to 0. Also, from the object function, there's no linear term about W. C is equal to 0. So how to solve in SVM? Just run X. You just run quadratic program for MATLAB, for example. It is suitable for when the sample size is not so big. The data you have is not too big. You can use a quadratic program. And if you have very, very large sample size, maybe you want to using some method that it's designed to solve SVM. For example, SNO, something like that. Okay, so far so good. Okay. And
after the previous one, what happened? So it's greater than equal to 1. What happened to 1?
sorry.
It's greater than equal to 1, right?
Where are you seeing?
Subject to yi is greater than equal to 1.
Yeah.
But where is the 1 showing up? Or
Sorry, I forgot the one. B should be yi times b0 minus 1.
oh, okay, so it's supposed to be in the B. Okay.
Okay, sorry.
Okay.
It's a typo. And any questions? Okay, so we finished. You're done. Yeah.